Okay, so let's start the second half of the tutorial. Thanks for coming back. I'm Francesco Bonchi, and I will drive you through part 3 and part 4 of this tutorial, in particular part 3, which is the largest one, which is covering the literature about fairness-aware data mining. We mean by fairness-aware data mining, we mean the problem of developing a data-driven decision-making process which is non-discriminatory by design. That means that we have the usual machine learning process. So we have a database that fits a machine learning algorithm that builds a model which is then used for decision. Sorry. Okay, so as we have seen in the first part of the tutorial, our data set can contain some discrimination. Discrimination which can be of different nature, of different reasons, different forms. We abstract here, we don't care about how it is that the database contains some bias. We just worry about the fact that this bias can propagate through all the process, arriving to, till the end of the process, so by making our decisions discriminatory. Why this happens? Because the algorithm is designed just to find the discriminatory pattern in the data. So, sorry, the machine learning algorithm has no discriminatory purpose, but is designed to find what is contained in the data. So find patterns and then build models which are used for decisions. So if the data contains discriminatory patterns, this will not be stopped by the machine learning algorithm. Actually, this will be propagated or even amplified in some cases, okay? So if we don't do nothing in this process to block the propagation of bias, it will arrive till the end in our decisions. So we need to block it somehow. And we have 3 possibilities in this case. For instance, sanitizing the data set. So going to check where are the discrimination patterns in the data and fixing in the data. We call this a preprocessing approach, so in a preprocessing phase. If we do so, then we can apply any machine learning algorithm because we are already guaranteed that the source of discrimination of bias, it has already been blocked in the preprocessing phase. Second choice is to really go and modify the machine learning algorithm, so to make the algorithm aware of the potential of discrimination and fix it. The third approach is post-processing. So at the end, we build the model, we go check the model, find the possible sources of discriminatory decision, and fix the model. So in the rest of the part 3, we will use this categorization to also categorize the papers in the literature in pre-processing, in processing, and post-processing. So this categorization is by no means intended to be completed. It's also not rigid in the sense that some papers can also present more than one technique, so might belong to more than one class. Before starting covering the literature, I want to highlight some common aspects of all these papers, of this literature. First of all, the goal is the common one, which is to develop non-discriminatory decision-making process while preserving as much as possible the quality of the final decisions, okay? So if we think about a classification problem, we want to maintain as much as possible the accuracy of the classification. So all these problems, all these papers will have to face, to deal with the trade-off between achieving fairness and maintaining data utility. And all these papers have some common structures or common steps. So they start by defining some constraints, some measure of anti-discrimination or fairness that they want to achieve. They will present their transformation techniques for data, algorithm, model, depending if it is pre-processing, in processing, or post-processing. And then in the end, they will have to measure the utility which is remained in the data or in the model, okay? So let me get started with the pre-processing part. Here we will cover these 4 papers. There are others, but I will mention later. Okay, let's start with this paper by Feldman and others, KDD 2015. So this paper that was already briefly mentioned in part 2 present both a technique to certify the existence of discrimination patterns in the data, and then techniques to remove these discrimination patterns from the data. So I now focus only on the removal part, okay? So you can remember it was the end of part 2 that they define the measure of discrimination based on the predictability, so on the potentiality of predicting, so reconstructing the sensitive attribute like gender or race from the other attributes, okay? So here the purpose is to transform our data so to remove the input. In particular, we have like a database with X is the protected attribute, Y are all the other attributes, and C is the class, right? Like credit approved or not. So they aim at modifying only all the other attributes, so the Y. In particular, the goal is to preserve rank within each marginal distribution for each value of the protected attribute. So in this example, suppose this is SAT, which is like the usual test for entering college in the US, and suppose that X, the protected attribute, is gender. So you have male and female, and for instance, the blue curve, the blue distribution could be the female scores, and the red distribution is the male score. In an extreme solution where you really want to avoid any potentiality of using SAT to predict the gender, they create like an average distribution with the nice property that for each group it is preserved the ranking, okay? So more formally, you have the distribution for SAT score, so for the Y, for X equals Y, so for female and male. You have the CDF, and essentially they show that if you take the inverse of the CDF, so you take like the quantile function, so f minus 1 of, for instance, 0.5 gives you the score of SAT, so that, for instance, for female, it's exactly dividing into the group, right? So if you take the median of this quantile function for all the Y, so in this case would be for all the I, so it will be for male and female, what you obtain the distribution which is exactly minimizing the sum of distances using earth mover distance from all the distribution. So intuitively, you can think about this as a problem of rank aggregation, which is a nice problem in data mining. You have different ranks, in this case, for instance, for female and male, and you want to create a new rank which is close to all of them as much as possible, okay? So this is high-level intuition. So they show some nice experiments on 3 data sets. Here you have, on the Y, you have the utility maintained in the data, and on the X, you have the disparate impact, so the level of discrimination. And you see all the data set starts with some illegal level of discrimination. They put the bar between illegal and legal at 0.8, like the 80% rule. And you can see that by applying their transformation, they define 2 different algorithms. I didn't give the details, but by applying the transformation, they can move, they can reduce substantially the amount of discrimination in the data without losing too much utility, okay? In some cases, for instance here, the repair algorithm overdo it, and for instance, it creates discrimination on the protected group. So in this case, it arrives to discriminate males, but then it goes back to non-discrimination. So this was the high-level idea of this certifying and removing disparate impact. Now we move to a new papers by Kamiran and Calderts, published in KAIS 2012. So in a journal, this is is a journal paper collecting like 3 previous conference workshop paper. So data preprocessing techniques. Okay, here the discrimination measure is very simple. Essentially, you take the difference in probability of the 2 groups. Let's keep thinking about gender and male and female, which is easy to remember. So this is the probability for males to get a positive outcome, and this is the probability for female to get a positive outcome. Okay, so the discrimination measure is the difference in this probability, and the goal, as usual, is to minimize the discrimination while maximizing the accuracy. Usually, this is done by giving some tolerance, some epsilon for acceptable discrimination, and you try to maximize the accuracy that you preserve in the data. And they study and compare 4 techniques. The first one is just for baseline, that is suppression. We have already said that just removing the sensitive attribute is not enough to avoid discrimination because of correlation with other attributes. So here in some experiments they remove the sensitive attribute, so the gender for instance, and also the top k attributes most correlated with it. And then the 3 proposed techniques, which are massaging, rewaving, and sampling. So this is the example that they use in their dataset. So a small job application table with sex, ethnicity, degree, job type, and the class. Okay, so massaging, the idea is to rank the individuals using a ranking algorithm with respect to the probability of having a positive outcome, and then essentially swapping the labels of some individuals which are close to the border, so to arrive to a balanced situation between the 2 genders. This is also another slide presenting the overall idea. So first you learn a ranker, and then you relabel some, so for instance, some males that were in the positive sides with respect to the boundary are relabeled on the negative side, and some women are relabeled on the green side. At this point, you are certified that your data set has no longer discrimination. You can learn any classifier. Okay, rewaving, it's another technique that gives different weights to different individuals, so to neutralize the discrimination effect in the data. So how do we reweight? Essentially, the weight that you give to every class is, so every combination of gender and the outcome in this case is the ratio between what would be the expected, assuming that there is no discrimination, and what is instead observed in the data. So it's easier to, with an example. So the probability of being of gender female if the class is positive, if there is no discrimination, so there is no gender bias, there is no correlation at all between the outcome and the gender, right? So this conditional probability would be just the product of the probability. So in this case, it's 0.5 because you have 5 female, and 0.6 because you have 6 positive outcome. Okay, so this means that you would expect 0.3 probability of positive outcome for females. So that means that you would expect to find here 3 females with a positive outcome. Instead, in the data set, there are only 2, okay? So essentially, we weight females with these 2 females in the data set with positive outcome, we weight 1.5 instead of 1. So to achieve these 3, that would be the expected weight in case of no discrimination. And you can do the same for the other 3 combinations, okay? So this is the idea. So the next technique, sampling, start from the same idea of rewaving. Essentially, for the 4 groups, ERDP means deprived positive, so like female with positive outcome, female with negative outcome, and the group is favored positive and favored negative. So for instance, male with positive outcome and male with negative outcome. So the idea is the same. We compare the expected sides of these groups with the actual sides of those groups in the data, and we use this fraction as a sampling probability. And then we sample from the points that we have, possibly duplicating data points. And they propose 2 different ways of sampling. Uniform sampling, so you pick according to these probabilities uniformly at random. And the effect is that, for instance, some female with negative outcome might not be sampled, so they are kind of removed from the database, while some female with positive outcome are duplicated, because you can pick more than once. And the same for males with negative outcome are duplicated, and males with positive outcome are removed. So this uniformly in the space. Then there is preferential sampling that follows the idea that we have already seen before for messaging of taking individuals which are close to the decision boundary, so that the quality of the classification that we are going to build is less destroyed and maintained. They have some experiments. Here, no means no preprocessing. So they build a decision tree on the original data sets, and you have this amount of discrimination and this accuracy. Then no SA means no where the gender has been removed. And then you have the other techniques, reweighting, uniform sampling, preferential sampling, and massaging with some ranker before. You can see that just removing the gender from the dataset does not make any difference at all with respect to discrimination and accuracy, while more or less all the proposed techniques reduce drastically the discrimination, while losing only very little in terms of accuracy. Okay, so this is the idea. So the third paper is by Sarah, which is our tutorial co-author, which could not come today. So a paper together with Josep Domingo Ferrer at TKD 2013. So they propose a framework to measure and to then remove discrimination from the data. And this is based on classification rules, which are like association rules, where in the head you have the class. We have already seen this in the part 2 of the tutorial. And we have already seen various measures like extended lift in the first part of the tutorial. And this concept of alpha discriminatory, if one of these measures is above a given threshold alpha, or alpha protective if they are fine. So if the amount of discrimination doesn't reach the threshold alpha, okay? So the idea is to use classification rules as a way of detecting the patterns of discrimination in the data, so that then we can go and fix these patterns in the data. So to have a data set which no longer contains discrimination patterns. So the data transformation should achieve the goal of removing all potentially discriminatory rules while having minimum impact. So the answer that they have to give is which records should be changed, how many of these records, and in which order. Okay? So which records should be changed? They propose two rules. two techniques which are somehow similar to the ones we have seen also in the previous paper. In one case, we change the sensitive attribute, so we change, for instance, a male to female in the records which are granted credits. In the rule number 2, instead, we change the outcome, so the decisions. For instance, change grant credit to denied credit in records with male gender, or the other way around, from denied to granted in records with female gender. Okay, so very simple techniques. And the important point is that they have a theorem showing that making this type of fixing to avoid discrimination rules does not produce other rules. Other alpha discriminatory rules. So by fixing our data set, we are not going to produce more discrimination. How many records should be changed? There is also there is a closed formula that says given alpha, if you want to fix this rule, this is the number of supporting records. So the records in the database that support the rule that you need to change. So I don't know, I will not go into the details of this. In which order records should be changed? The idea is to find the set of records in the database that support the rules, count how much impact will produce changing these records, and then change them in order of minimum impact. So essentially, we find all the records that support these rules, and then for each of them, we compute the number of other rules, other frequent rules, which are supported by the rule. Okay, and then essentially we fix according, in this case, to the rule of changing the gender, how many were given by this formula according to this ascending impact. And well, this is the whole idea. So the fourth paper that I'm going to present in the preprocessing approach is by Ziobeit, Kariman and Calderts as ICDM 2011, and it is about handling conditional discrimination. Because all the techniques that we have seen so far, they just aim at removing all observed discrimination. But the point of this paper, which was already also discussed by Carlos in the first half of the tutorial, is that there is always some part of the discrimination which is kind of legitimate, which is explainable, okay? And if we try to fix the whole discrimination without taking this in consideration, we do a double damage, because on the one hand, we decrease the quality, so the utility maintained in the data and the quality of the models that we are going to build from the data. And on the other hand, we can also create reverse discrimination, because we are trying to fix a discrimination which is not a real discrimination, and this could produce discrimination on the other group, okay? So this is the example. Consider college admission applications. You have 1,000 male and 1,000 female, and the outcome is that 360, so 36% acceptance rate for males, and only 24% acceptance rate for female. If you just look at the acceptance rate, you might believe that there is a gender bias, okay? But all this difference in acceptance rate is completely explained by the fact that females tend, in this example, tend to apply to the more competitive program, which is medicine in this case, okay? If you see, 80% of females apply to medicine, while 80% of male applies to CS. And medicine has a 20% acceptance rate, and CS has 40%. So in this case, there is really, if you break down by program, you find out that there is no real discrimination going on, because actually the two genders have exactly the same acceptance rate in the two programs, okay? So this example is based on famous Berkeley 73 case, where there was a really a legal case because there was apparent discrimination against women, but when you go break down by departments, there was actually a light bias in favor of female in most of the departments. Okay, so in the real world, it will never be totally black or totally white. So in most of the cases, we will have some discrimination which is explainable together with some real bad bias. Okay, so let's consider this example. In this case, again, we have 1,000 male and 1,000 females, and they have the same application pattern as before, in the sense that females keep applying more to the more competitive program, which is medicine, and these give us some explainable discrimination, as we have seen before. But at the same time, we can see that female have a lower acceptance rate even if we break down by program. So it's no longer as before, they were exactly the same. So in this case, we really have some explainable discrimination together with some bad gender bias. So of this 22% difference in acceptance rate, it's a very natural question to ask in which part it is explainable and in which part it is instead bad discrimination. Okay, so we'll answer this question. The first step toward answering this question is deciding what should have been the acceptance rate for a given program if there was no bias. So the author discussed two possibilities. The first possibility is to take the observed acceptance rate. So for instance, for medicine, let me go back one slide, it would have been 17%. But if we do so, this would lead to redlining, because somehow we will prepare the data in such a way that the machine learning algorithm later will learn that the programs which are applied by females are more competitive, and in turn will give like lower acceptance rate by the model itself. It's really like the example we saw in the first part of the tutorial of redlining, that you have for giving credits, you have a model that says that people living in a specific suburb of the city have a bad credit history. And you model it, and then your model in the future will keep giving a bad credit score to people just because they live in that suburb. Okay, so this is exactly the same situation. If we do so, we would just move the gender bias to discrimination at the level of program that will act as a proxy for gender. So the right way of doing this, of deciding what should have been the acceptance rate for a faculty, is to take the average between the two genders. Okay. And then in this way, we can go and measure the explainable discrimination and the bad discrimination as the difference between the total observed discrimination and the explainable one. So let's make an example which is easier. So as we said, we take the average between the two genders. So we say that the correct absence rate should have been 20% for medicine and 40% for computer science. So given this correct acceptance rate, we can measure the amount of explainable discrimination, which is due to the fact that females apply more to the more competitive program. So we see that 20% of males apply to the 20% acceptance rate program, and 80% applies to the 40%. Instead, this is for female, 80% apply to the 20% acceptance rate, and 20% to the acceptance rate of 40%. So this gives us a 12% explainable discrimination. We observed 22% of total discrimination, so we can say that 10% of discrimination was bad discrimination. Okay, so the next step is measuring to what extent the discrimination which is present in the data is modeled, so is carried over by the machine learning algorithm. In particular, they use decision tree. And they use synthetic data which is generated by this belief network. You have a test score which is picked uniformly at random between 1 and 100 for each individual, and then you have this formula deciding whether you get accepted or not. So in particular, you have A, which is modeling the effect on acceptance decision due to the program picked, and B, which is modeling the acceptance decision due to gender bias. And as before, you have half of the people male, half of the people female, half applying to computer science, half applying to medicine. What is kept variable is the amount of men or women that apply to the more competitive program. So this alpha 1 minus alpha. So here it is reported 3 cases. Case 1, which is only explainable discrimination. Case 2 is only bad discrimination, and case 3 is a combination of both. And you have in the data, first column, and after training a decision tree in the second column. So in case 1, you have only explainable discrimination through program. So you have 0 bad discrimination, and you observe discrimination based on who applies to the more competitive program. So in particular here on the left side you have more male applying to medicine, and here on the right side you have more female applying to medicine. So you have like positive discrimination means discrimination on female, and under 0, below 0 means discrimination of men. So the green line is just reporting who applies to the more competitive one, and is perfectly, as we said, explainable, so we have no problem. And also the model that we build reflect the data exactly. So more interesting is the second case where we have gender bias, okay? So we have bad discrimination, and in this case is only bad discrimination, so the red line and the green line are completely overlapping and flat in the data. When we go modeling, this is the interesting thing, the decision tree, even if it has no access to gender, is using program as a proxy for gender, so is doing the redlining. So it's taking the gender bias, and even if it is not seeing the gender, through program as a proxy is discriminating. So you see it's always above 0, so it's discriminating female. And the only point it goes to 0 is here when you have beta equals 0. That means that exactly 50-50 between male and female applies to medicine and to computer science, so that there is no correlation at all between the program and the gender. So the decision tree, as it is only accessing program and no gender, has no way of discriminating. So this is the only case in which goes to 0. So the third case, you have a bit of both. So a bit of good discrimination and bad discrimination. So you have, in the data, you have the bad discrimination, and you have the same observed discrimination that goes just a bit higher, because it's summing up the good and the bad discrimination. The decision tree, again, is discriminating. So even if it is not accessing females, gender, is still discriminating against female. And this is also interesting. The total observed discrimination is like tilted, because it goes higher here because it's summing the good and the bad discrimination, because here is the point where female applies more to medicine. If we go at the other extreme, where male applies more to medicine, so to the more competitive one, male ends up having like a lower acceptance rate in total, in global. So you have this sort of appears like male are discriminated, even if in reality there is bad gender bias against female. So this is the so-called Simpson paradox. This is also the motivation why we had this Berkeley 73 example. So when you go breaking down in subgroups, you can find actually reverted discrimination with respect to the apparent one that you have at the global level. Okay, this was interesting. So then they propose methods, local methods to change the input data. These are similar to the method from the same author, massaging and preferential sampling that we have seen before, but they are local. Local in the sense that they apply to each partition of the explainable attributes. This would mean that they would apply to computer science and to medicine in isolation. And the idea is that by applying local methods instead of global methods, you maintain more quality in the data because you don't try to fix also discrimination which is only apparent. And this is confirmed in the experiment. So you have global techniques, which were the one we saw before, tend to overshoot when there is large part of discrimination that can be explained. Okay, let's switch this one. There are also other approaches that I've not covered here that can be considered preprocessing. This will be briefly mentioned again in the part 4 of the tutorial because these are interesting approaches that tackle the problem of discrimination and the problem of privacy preservation jointly. Okay? So let's move on to the in-processing phase, so where we try to change the machine learning algorithms so that they are aware of the discrimination. We'll present briefly 5 works here. There are many more. For instance, these 3 that I'm aware of and I'm not going to cover, and probably there are even some more. Okay. So first work by Kariman et al. CDM 2010 is discrimination-aware decision tree learning. So again, we have the same setting. We have like a protected attribute. Let's keep continuing thinking about gender. And we want to minimize discrimination while maximize the predictive accuracy. As a first step in this direction, the authors studied the decision tree, and they proposed 2 possible fixes to the classic decision tree induction algorithm. One is changing the way we split, and the other one is changing the label to leaves. So if you remember the classic decision tree induction algorithm, at every node you need to pick the next attribute to split further the tree, and you pick the attribute that better discriminate with respect to the target variable, so to the class variable. And you keep doing this until a node reaches some level of purity. So it has like a majority class which is dominating. At that point, you might stop and assign the label which is dominating to the leaf. So the author proposed to keep in consideration also the sensitive attribute. So when we go selecting the next splitting attribute, we do not only try to maximize information gain, but also to minimize the information gain with respect to the sensitive attribute, so with respect to the gender. And they try different combinations for each fraction or the difference, okay? So this very simple idea. Essentially, the algorithm remains the same. What only changes is when you go measuring the quality of a possible split, okay? So the other idea is to build the tree till the end. This produces a division of the decision space in the leaf nodes, and the classic algorithm will assign the majority class present in each leaf node. And here the problem is to change some of this label, okay? So changing the label to a leaf node would produce, hopefully, a reduction of the discrimination, which we will have to pay also with a reduction of accuracy. So the problem becomes to select the leaves that we are going to change the labels, okay? So that we achieve our discrimination goal without reducing too much accuracy. So they show that this problem of leaf relabeling is equivalent to a knapsack problem, which is a classic NP-complete problem, but which has a good approximation algorithm by Greedy. So the problem is you are given a knapsack of size k, you have a set of objects which have both weight and size, and you want to find a subset of the object that fits in the knapsacks, so by size, and that maximizes the outcome, so the weight. So why this is how can this be applied to leaf relabeling? So first of all, we do not consider potential leaf to be relabeled if by relabeling without we do not gain nothing in terms of reducing discrimination. So in this example, relabeling 5 and 6 will only produce reduction in accuracy and no reduction in discrimination, so it doesn't make sense. They are out of the game. Now we do the knapsack game, which is selecting the nodes that we are not going to relabel. Essentially, suppose we have a current discrimination of 20%. If we relabel of these 4 leaves, we will reduce by 50%. So this is too much, we say 30% can stay. So 30% becomes the size of our knapsack, and we want to find the leaves to maintain, okay? So to maximize the accuracy. If we take L4 together with any of these others, we will achieve a maximum of 25, while instead if we take L1, L2, L3, that again gives 30, we do 35, so we do better. That means that L1, L2, L3 will be the result of our knapsack, and this means in turn that L4 is the leaf that we are going to change the label, okay? And we relabel L4. So this is the technique of changing the label to leaves in a decision tree. Caldertz and Werber also proposed 3 approaches to modify naive Bayes. I will show them very high level again. So the idea of the first method is the modify naive Bayes here, right? Instead of having the probability of the class times the probability of S, where S for us now is the sensitive attribute, given the class, we swap them. So we have probability of S and probability of C given S, okay? So, and then we go and alterate the probability of C given S until there is no more discrimination. It creates a direct discrimination-free naive Bayes, but it does not avoid indirect discrimination through, for instance, attribute AS that could be potentially correlated with the sensitive attribute S. So the second model solved this by essentially building 2 naive Bayes models. So if S has 2 values, suppose S is gender again, this means that we produce separately a naive Bayes model for female and a naive Bayes model for male. So this way, there is no possibility for AS to be used to predict the gender because they are separated. They are 2 different models. The third model, a bit more sophisticated, uses a latent variable. So the idea is to try to model the actual class labels that the dataset should have had if it was discrimination-free, so if there was no discrimination. And this is modeled by a latent variable L. So the assumption is that L is independent from S because there is no discrimination, right? And C, which is the observed outcome that we see, is a combination of both what would have been the real outcome if there was no discrimination and, in this case, the gender bias, if S is gender, okay? So we have this model and we fit the parameters by expectation maximization. Okay. The third paper that I'm going to present in this in-processing part is by Zafar et al. Fairness constraint, a mechanism for fair classification. The authors part here from the disparate impact doctrine of 80% rule, and well, they say it's not always the case that is 80%. Sometimes the proportion could be different, but the goal is to produce a fair classifier. So a classifier whose output achieve a good proportion in the positive graphs for the different values of the sensitive attribute. So the key idea here is to limit the cross covariance between the sensitive feature value and the distance from the Decision boundary. This is easier to see in a figure. Okay, consider this classification task. Here you have the Decision boundary, so an hyperplane that in this case is a perfect classifier, right? Divide perfectly in the two classes, which are the crosses and the dots, but it is unfair with respect to the colors. Suppose color is the gender, and suppose that green is female and blue is male. So in this case, you would have like males, which is 7 out of 12. So we will have a 58% acceptance rate for male, while for female is only 1 out of 4, so 25 acceptance rate. By moving a bit this decision boundary, that this can be achieved by this fairness constraint, we can have, of course, words classifier when examined in terms of pure accuracy, because it's now making a couple of mistakes like this one and this one that it was not making before, but is now fair. Right? With a small cost in terms of accuracy, now it has a 50-50, because females are 2 positive and 2 negative, and male are 6 positive and 6 negative. So these constraints, again, that limit the cross covariance between the sensitive feature value and the decision from the decision boundary, so the hyperplane, and it's okay, constrained by this constant C, which is used for handling the trade-off between fairness and accuracy of the classifier. And this can be applied to all classifiers that can be represented as these hyperplanes and as a constrained optimization problem. For instance, the logistic regression, we can just inject the constraint, and the key point here is that this problem can be solved efficiently. And the authors also very briefly, not only in my presentation, but also in the paper, they show that this can apply as it is also for hinge loss classifier or for SVM. Okay, I show you some example. So here on the X, some experiments, sorry. Here on the X, you have this threshold C. So the smaller it is, the more stringent is the constraint. And you can see here that as we go closer to 0, the percentage in the positive class, so positive outcome for female and male get closer and closer. These another experiments where on the Y we have accuracy on a test set, and on the X we have the ratio between male and female in the positive class. So at 1, it means that we have exactly the same number of male and female in the positive class, and it compares with two baselines, and well, using the constrained algorithm, so the algorithm proposed by the authors, we can achieve fairness with a smaller loss of accuracy. And well, again, the same concept. As you go closer to 0 for C, you have higher fairness, and you lose a bit of accuracy. And this can be applied also to multiple features, for instance, mixing gender and races, and everything applies exactly as it is. Okay, so I will conclude this part on in-processing approaches with two works by Cynthia Dwork and colleagues. These are two works rather theoretic in nature, and with the second one building on top of the first one. So the first one is Fairness Through Awareness, as ITCS 2012. So the authors start motivating their work with an example in advertisement setting, and they start from a Wall Street journal that shows an example of a vendor, in this case Capital One, which is presenting to first-time visitors to their website different credit cards based on a profiling of the visitors, so of the individuals, which is done by a tracking network company, X+1, which tracks the behavior of individuals on the web and collect all sorts of demographic and information. And so the concern here, besides privacy, which is already a big concern, is steering that we have seen in the first half of the tutorial. So this way of presenting, so moving some protected group towards less favorable credits offers, okay? So because you present different credit card in the moment they arrive to your web page. So this is the setting. We have individuals. The ad network has a classification algorithm that produce outcomes, and then these outcomes are used for doing business decisions and actions by the vendor. And the goal, as it has been so far, is to modify the classification algorithm so that once that the outcome is passed to the vendor, it has no longer possibility of doing discriminatory activities. Before presenting their proposal, they go and discuss various alternatives. The first one is, again, just removing the protected attributes. We already seen again and again that is not enough. Much more interesting is a critics to group fairness. So group fairness that we have seen to a large extent, which has been the most studied type of fairness by the largest part of the literature. In this work, they show several examples highlighting the fact that is an insufficient notion of fairness if taken in isolation, as Carlos already discussed before. Especially, they take many cases in which you have apparent statistical parity between the two groups, but the outcome is really unfair at the level of the individual. So in this work, they focus more on the individual, and the key point that they do is that fairness requires awareness, in the sense that require understanding a priori of the classification task that we are addressing. So this is where the awareness in the title comes from. And their high-level goal is individual fairness, so is treat similar individuals similarly. That in the case of the classification task means similar individual with respect to the specific classification task should be treated similar in terms of the outcome of the classification. So again, you can see that they assume a priori awareness of this classification task, and not only, there is a much bigger assumption that we are able to have a distance matrix which depends on the classification task and that is available a priori. So this is the biggest assumption of this work, that this similarity metric can be known a priori. It ideally should capture the ground truth, and it should be transparent, open to public discussion, and potentially to refinements. They also discuss some types of metrics that are existing in the real world to justify that this vision of this known metric and open is not so science fiction after all. Okay, more on the technical stuff. So the formal setup here, a classifier is a randomized mapping function that map individuals to outcomes, or alternatively to distribution over outcomes, to probabilistic distribution over outcomes. And the individual fairness constraint is expressed by this Lipschitz condition that says that the statistical distance between the distribution of outcomes of two individuals, X and Y, should be limited by the distance of X and Y. So this is the optimization problem. You have an arbitrary utility function defined by the vendor. You want to maximize expected utility because we have a randomized approach, and such that we satisfy the Lipschitz constraint. Okay? And they show that this can be solved by linear programming, so it can be solved efficiently. There are many more contributions in these very interesting papers. So as I already said, this contribution of discussing the inadequacy of group fairness or statistical parity. They also study the connection between individual fairness and group fairness, that is, in which cases satisfying this Lipschitz condition also implies having group fairness, and they have a result that shows that if the Hertz-Mover distance between the two groups is small, then having individual privacy also implies, individual fairness also implies group fairness. Then they also study when this is not the case, so when the individual fairness does not guarantee the group fairness, how to enforce this. And finally, they also highlight an important relationship with privacy. They show that the proposed definition of individual fairness is a generalization of the notion of differential privacy. So it's very interesting reading. The second work, more or less by the same group of authors, which is presented at ICML 2013, Learning Fair Representations, start from the limitation of the previous work, so limitations of fairness through awareness. A big limitation is these assumptions of the distance metric that is assumed to be given and known a priori, and this might not be always the case in the real world. And moreover, another important limitation is the way the problem was formulated in the previous paper was not a learning framework, in the sense that the mapping was given for a set of individuals, let's consider the training set, but there was no way to generalize this to new data, so to new individuals. So it was not really a learning setting, okay? It worked only for training set, to make it simple. Okay, so the high-level learning fair representation extends this first work in several important ways. First of all, it developed a real learning framework, so learn a general mapping that is then applicable to any individual, also unseen, so new individuals. It learns a restricted form of a distance function as well as the intermediate representation of the individuals. So there is no longer the need of this distance function to be given a priori because it's part of what is learned by the approach. It achieves at the same time both group fairness and individual fairness. This intermediate representation can also be used for other classification tasks. That is to say that transfer learning is in principle possible. And while the previous paper was totally theoretical, this work also has some nice experimental assessment because they create a real learning framework so they can do experiments on some test data. main idea at high level is to map each individual to this representation, so a probability distribution in a new representation space, and this representation space should be designed such that it loses any information with respect to the membership of individuals to protected subgroups while maintaining as much as information as possible. So fairness becomes an optimization problem of identifying this intermediate representation that best encode the data while making it impossible to reconstruct the membership to the protected subgroup. So this is the authors say this is a general idea that could be applied in many different ways. So in making many different intermediate representation. In this paper, as concrete tool that they propose as this intermediate representation, they take a probabilistic mapping to a set of prototypes. So this can be seen also as a form of discriminative clustering model. And for sake of time, I omit the details. Okay, so post-processing approaches, there is not much in post-processing approaches, not as much as in processing and pre-processing. I think this probably is a bit less appealing because if you build your own model and then you try to go fixing the possible source of discrimination, when the model is already built, somehow you might damage it too much, right? So you might lose too much accuracy. So intuitively, it's more appealing to solve the problem earlier on in the process. However, we already seen an example because when we were presenting the discrimination-aware decision paper, there were two approaches. One was the change in the splitting criteria. The other one was relabeling leaves. And this relabeling leaf can also be considered a post-processing because by all means at that point the model is completely built, at least a first version of the model. Then we go fixing part of the model, which is the labels assigned to the leaves. So this could be also considered a post-processing approach, even if I already covered it before. There is also another paper by Sarah and collaborators that was presented in the Data Mining Knowledge Discovery Journal in 2015, and that I'm going to present now, Discrimination Privacy Aware Pattern. And as said before, one very nice idea is to deal with privacy and discrimination jointly, right? In this case, they study the extraction and publication of association rules from a database, in this case a database of credit history, and suppose that we extract frequent patterns that have a support larger than a minimum support parameter k for purpose of k anonymity, and if we just consider privacy, we might publish rules that have very high support, but that could be used for discrimination, right? Like gender, female, credit approved, no. At the same time, if we focus only on discrimination, we might publish rules like these two that say veterinarian salary low and credit is denied, and this support is 40. And another rule that say veterinarian credit approved no, support is 41. If we have a K, a minimum support of, let's say, 30, we might think that these rules are safe because they don't pinpoint any individual in the data. But as we showed in a old work, you can use the support of this rule to say that job veterinarian, salary high, and credit approved equals no is only one. So that means that in the data set there is only one individual, which is a job veterinarian, which has salary hike, and if I know a veterinarian with salary hike, I might discover from the data set that he had a credit denied, okay? And this could be personal information that we don't want to disclose. So there are these two problems that need to be solved before we are able to use our association rules. And this is a bit the system that they propose, that is first sanitized with respect to privacy and then sanitized with respect to discrimination. Why this order and not the other order? This is the main results of the paper. They show that by sanitizing, by applying anti-discrimination sanitization to have alpha protective patterns, rules does not generate new discrimination as the result of its transformation, and also the same anti-discrimination pattern cannot produce any non-k-anonymous pattern. So from patterns which are k-anonymous, it cannot produce non-k-anonymous pattern. So instead, if they would have used the other way around before fixing discrimination and then thinking about privacy, that would haven't worked, because in the second step they might improve or make it worse the situation with respect to discrimination. Okay, and well, other thing, they show that privacy pattern sanitization based on either k-anonymity or differential privacy can work against fairness, and they propose this anti-discrimination pattern sanitization method then do not interfere with the k-anonymization of the patterns, and they show that the utility loss caused by simultaneous anti-discrimination privacy protection is only marginally higher than the loss caused by each of those protections separately. And that's it for part 3. I will now have 10 minutes of conclusions, and then we can have a discussion. Okay, so challenges in this interesting hot topic of research. We have seen the trade-off between achieving fairness and maintaining utility on the data, but this utility of the data is hard to assess, because we compare against the utility that we would have using the data set as it is, but this training data is biased, so the situation is complicated, not only for achieving discrimination, but also to assess how we are doing. There is also a lack of data set and benchmarks. There are very few data sets, as we discussed in the first part of the tutorial, and they are always the same. When I was showing these examples, I was not saying if it was German credit or census, but they are always these rather small and rather artificial data sets. So this is also a problem that the community will need to address in the future. As we already said, that there is a jungle of different definitions, and unlike for the case for privacy, where things have become more clear over the years, anti-discrimination legal concepts are still very diverse and vague. In the first half of the tutorial, we discussed all these different definitions. So this produces the situation in which different researchers take different definitions, and there is no single agreed upon measure for discrimination. And this, of course, brings to the definition of different data mining problems and different machine learning algorithms. Very interesting is the interaction of us as a research community with the legislator, so those one defining the regulation. So this is like for the case of privacy, this must be, let's say, a collaboration beneficial for both sides. On the one hand, laws give us the rules of the game, so it provides us the definition, it provides us the objective functions, the constraints, that we should keep in consideration while designing algorithms, right? But at the same time, our progresses, so new technological development, should be carried to the attention of the legislator that should take this in consideration while designing new regulation. However, this communication channel, as often happens, is not very clear. So if I come out with a new algorithm, I can think, is my data transformation algorithm legal? Can my discrimination detection have some real impact in the real world? So in some case law. But with all this variety of definition in the legal side, is quite difficult for somebody with a background in computer science to navigate. So this highlights also the importance of collaborating with legal people, but also with sociologists, and in general, the importance of multidisciplinarity research. As usual, as is the case for privacy-preserving data mining, there is many differences in regulation between USA and the EU, so also this creates additional confusion. Regarding EU, it's very interesting that it has been published and it has been defined, adopted in this spring, the new General Data Protection Regulation, GDPR, 2018, because it will enter in application in 2018, and it will replace the old Data Protection Directive that most of the research in privacy was referring to. And this is very interesting results from the European Commission, whose goal is to give back to the citizen control on their personal data. And it deals with concepts such as consent, responsibility, accountability, right to be forgotten, and so on. So many interesting concepts that can be translated in constraints for us. So a very nice example is the right to explanation, but this applies to other concepts as well. And the point is that this type of constraints that come from the regulators will pose large challenges for industry, because there is really a gap between the current status of technology, the current status of how things are done in the business world, and those constraints defined by the regulator. But while this poses big challenges for the industry, it creates great opportunities for us that we do machine learning research to take the lead in designing algorithms, in taking these constraints from the regulators, and in advance, and also help the industry to be compliant with this request. In particular, this right of explanation, but again, as said before, this applies to other concepts. The right of explanation is very nice because it allows an individual that has suffered some decision to ask the explanation of the algorithm decision. So not only to ask the explanation of the decision, but really to see inside the black box, which is the algorithm. And these are very nice constraints for doing new research in machine learning, and there is already a very recent archive preprint paper which is digging into the details of this new regulation and what this implies for algorithmic design. Fairness and privacy, we have already mentioned various times that there is a clear interplay, but this interplay must be investigated further and must be exploited further. So privacy preservation, how do we prevent sensitive information from being leaked? While discrimination prevention, how do we prevent sensitive information from being abused? So the sensitive features in those contexts might overlap in some cases or not. For instance, I don't care about people knowing my ethnicity because it's very clear. Maybe I care about my, I don't know, religion or political beliefs, but I would object if ethnicity is used in decision making that might affect me. Okay? So when there is, when the sensitive attributes coincide, that might be a problem, because hiding the sensitive information might also make it more difficult to discover discrimination practices or discrimination patterns. This is a promising direction of research, is to try to deal with the privacy problems and the fairness problem jointly. Because as we said before, they share challenges, they have common techniques, and also they can help each other. So common challenges, for instance, is this trade-off between achieving the goal, which is privacy or fairness, while maintaining some quality in the data. And this is done by either modifying the data or modifying the algorithms. So they are very similar techniques and similar concepts. So it does make perfect sense to consider both jointly. And we have already seen something on this during the tutorial. We didn't present all the paper. For instance, there's this very nice work by Salvatore Ruggeri that shows that one of the notions of anonymity that were presented as improvement of anonymity, in particular the T-closeness as an improvement of K-anonymity, it also provides some form of fairness. Okay, so this very interesting results. I say, while if you massage your data in such a way to achieve privacy, as a byproduct, you are also achieving this form of fairness. We have seen also some work by Sarah about achieving privacy preservation and discrimination prevention, either at the preprocessing phase or at the postprocessing phase. And also we have seen the work fairness through awareness that have this definition of individual fairness, and they show that is a generalization of the differential privacy definition. Okay, some future work. The most obvious thing to say is that most of the literature that we have covered in the tutorial today to deal with simple binary classification like hire, don't hire, from normal relational table, but we know very well that not all the problems out there are a classification problem, and data can be much more complicated than a relational table. For instance, we might have to deal with multi-class or multi-label classification setting, regression settings, noise in the input data. Most of the work we consider were also thinking just about one protected characteristic, like gender, for instance. Some of them were already considering the case of multiply protected characteristics. This is an important extension. It also potentially missing information from protected characteristics, for instance, due to privacy. But as we know, the fact that the gender is not in the data does not mean that the data does not contain gender bias. Not only going beyond binary classification, but beyond classification in general. So, as I said before, not all problems are classification problems. So, it is needed to develop a general theory of algorithmic fairness, where algorithms can be any sort of algorithm, not only machine learning classification algorithm. For instance, it's especially with all the web applications out there, it's very important to develop fairness in recommender system and in personalization. It's also an interesting problem to be studied is fairness in social network data. Suppose that some hire, don't hire decision is based on the people you know, right? So how do you detect such discrimination practice? Or fairness in text data, for instance, develop tools to automatically detect sexist or racist comments in social media. Or this is very interesting, to develop practical tools as some that have been showed in the first half of the tutorial, like Add Fisher. There is another tool, Sheriff, which is very nice and is based on price discrimination. There is this thing, I don't know if you ever realize, sometimes I'm sitting on the sofa with my wife with two different machines, one laptop and one iPad, looking at the same website for the same flight and getting different prices. Is something happening out there? Just try it. You can download this Sheriff tool also. So also developing this type of tools is interesting future work. Before concluding, some acknowledgements. Here we have some names of colleagues that have provided us with their slides that we used in the tutorial, but there are many other researchers to which we didn't ask the slides because they were nicely available on their websites. We thank them all, and the tutorial was also supported by 2 projects, one European Union project about this type of problems in the business of advertisement on the web, which is named Types, and also Catalan project, so supported by the Catalonia Trade and Investment Agency, which is named Faraday. It is again about fairness in algorithms and discrimination. So, and that's all. The slides are available on the web page of the tutorial if you are interested. And thanks for staying all these 4 hours.